to adjust. There we go. Okay. So in this case, we now have two tools that we can use. We have the frequency of each of these alleles now, the raw frequency. Cool. Here's where the Hardy Weinberg equation is going to show us what we'd expect in a population with barely any gene flow, no change, just a normal, like non-changing population. This is the like quote unquote expected value. So this is kind of going to factor into your chi-square stuff. So remember, the Hardy Weinberg equilibrium rarely happens in real life. It's just a mathematical kind of totem, or kind of like a standard basically. So let's compare these numbers here. So over here, you'll see this equation written like this. So in this case, P, so let's say P equals R, Q equals W in this case, because remember, the alleles are going to change, but the equation itself is always going to be written like this. P squared plus 2PQ plus Q squared equals 1. These are the expected genotypes using this information. So let's fill out exactly what you would expect for each of these. So for double dominant, that's what this is. So this is what we're essentially saying is our double dominant. In this case, you have 0.585 squared. And what that equals is 0.0342. Yeah. So that's the frequency that you'd expect of double dominance. So that is, remember, RR. That's the frequency you expect, so about 34%. Here are your heterozygotes, because remember, you're getting one versus the other. And this is just a mathematical equation to say if you have these numbers, here's the equilibrium you'd expect the genotypes to go in. Okay? So 2 times 0.585 times 4.15. I know we're kind of getting over here. What this equals, do this math, and you end up 0.486. These are your heterozygotes. Okay? Last one. Here's your double recessives, and remember, we're working with alleles that aren't technically recessive, but that's usually what Q is going to say. But you'll be able to apply this the exact same. WW means that we're going to take the allele frequency of W, you square it, so you times it against itself, so 0.415 times 0.415. What you get is 0.72, or 172. So if you add all these up, they equal 1. These are the expected ratios in a population of each genotype. So these are different than the ones we observed. And that's why Hardy Weinberg is a good, like, expected value metric. This is what we would expect in a population with no change. So we can use expected values versus the observed values to see, is one of these genotypes advantageous? Has one of these genotypes recently got an influx of gene flow, for example? Okay, so let's take a look at our individuals. So, just like in your lab, the observed number of these was 15, 25, and 7. Remember, our total is 47. And remember, the HW frequency for each of these was 34.2%, 48.6%, 17.2%. So if you translate these into expected solid values, let's see what we get. So 47 times 0.342, nope, that calculator didn't work, times 0.342 equals, you'd expect, so these are your expected, you expect 16 in this population given the genotype or the allele frequencies, remember those. So for this one, you would expect that 48.6% of this population would be here. So 47 times 0.486, you'd expect about 23, so you can round up because you can't have like a half an organism or something. Okay, and then last one, out of this 47, you'd expect 17%, roughly 0.2, to have this genotype. Okay. Cool. So what we ended up having is, based on the equations that we ran and everything, and by just giving these numbers, and we had the genotypes already, you can eventually calculate from a population you observe in the wild, you can calculate the expected number of individuals and then compare it. In this case, these are pretty close. So this population is pretty even, and it doesn't seem like there's any advantage either way. You'd always expect a few more of these heterozygotes in a mixed population like this. So this is a good way to kind of take a look and see, okay, is this population kind of even? Is it changing? Because if you get expected numbers that are pretty normal, but for example, if we observed something like this, for example, it's like 2, 3, and like, what is that, 42? That's a huge number compared to the expectation. You'd think then maybe there's an advantage in being the heterozygote. So that's the kind of tool that you can use to say, okay, is there something wrong or different with this population? And that's how we can kind of check, is this population changing? Is something going wrong in the environment? It's a very good metric for that.